In actuarial science, retrospective and prospective policy values are important in establishing financial soundness and sustainability of insurance and pension programs. These values are critical in determining the reserves that insurance firms must set aside to meet their future obligations to policyholders. The prospective policy value is the present value of future liabilities, whereas the retrospective policy value is the sum of previous payments adjusted for the time value of money. Understanding these two variables enables actuaries to evaluate the current situation of an insurance contract and predict future commitments. The first identity is the prospective policy value. It estimates the present value of future benefits and expenses that the insurer expects to pay out, minus the present value of future premiums that the policyholder is expected to pay. It provides a measure of the insurer's current liability, considering all future obligations and payments. The prospective policy value is critical for ensuring the financial sustainability of insurance products. It is often used in the calculation of reserves that insurers are required to hold by regulatory authorities to ensure they can meet future obligations. The value serves as a forward-looking assessment, helping insurers gauge the adequacy of their current reserves. The second identity is the retrospective policy value. It refers to the accumulated value of premiums paid by the policyholder up to a particular point in time, minus the accumulated value of any benefits paid or expenses incurred. It essentially looks backward considering the financial transactions, premium payments that have occurred during the policy's lifetime. The retrospective policy value is primarily used to assess the fairness of a contract from the insurer's perspective. It helps determine whether the premiums collected so far have adequately covered the expected liabilities. This value is particularly useful for measuring the historical performance of a policy, providing insight into whether the pricing assumptions were accurate.
Now on to the premium difference and paid-up insurance formulas. We first tackle Identity 8.3, where we are introduced to the premium difference formula, which is useful for determining reserves. The premium difference formula is derived from the generic prospective formula we can recall from Lesson 6, where the present value at time t is equal to the net premium at time t multiplied by the present value of an annuity at time t. By factoring out annuity at the time t from this prospective formula, we obtain the premium difference formula. This formula expresses the fund required at time t as the amount needed to pay for a life annuity, representing the difference between the net premium needed and the net premium that the insurance company is actually collecting. In example 8.4, we can observe how the premium difference formula is derived when calculating for the benefit reserve of a fully continuous N-year endowment insurance. Now, we recall its prospective formula from the table under lesson 6.3, where t is less than n, that is denoted as follows. Now, by factoring out the expected present value of annuity, we obtain the following. This formula illustrates that the benefit reserve is the actuarial present value of a premium difference payable over the remaining premium payment term. It highlights how reserves account for the difference between the premiums required to fund future benefits and the premiums actually being charged under the policy. Now, with that in mind, let us try solving for example 8.5, where we will be calculating the net reserve for a 30-year term insurance of 100,000 on age 30 at the end of year 10. Let us start by deriving our premium difference formula by factoring out the expected present value of annuity from the given prospective formula. Now, we proceed to solve for the values of the premiums for a 30-year term on 30 and a 20-year term on 40, and the 20-year temporary annuity on 40. We can start by deriving the 20-year temporary annuity on 40 from the net level premium for a 20-year temporary life insurance at 40 and D. Now we can solve for the premium for a 20-year term on 40 as follows. We do the same for the 30-year temporary annuity and the premium on 30. And substituting the values, we have a 0.41 benefit reserve for a 30-year term insurance of 100,000 on 30 at the end of year 10. This may suggest that the policy is well-funded or that the future premium payments will sufficiently cover the remaining expected liability.
Moving on for Identity 8.6, we have the paid up insurance formula. This formula is derived from the generic prospective formula by factoring out A sub t, the actuarial present value at time t. This formula is expressed as the reserve at time t multiplied by the quantity of 1 minus the net premium at time 0 over the net premium at time t. This is a way to calculate the reserve for a life insurance policy, representing the APV of a portion of the remaining future benefits not funded by future benefit premiums that are still to be collected. Now let's illustrate with an example scenario. Consider a situation where a policyholder decides to stop paying premiums but wants to retain the same insurance coverage. In this case, the paid-up insurance formula is useful in determining the reduced level of coverage that the existing premiums have already paid for. This is also useful in understanding how much of the future benefit remains unfunded by the remaining premium payments. This formula shows us the reserve as the present value of future benefits not covered by future premiums. Example 8.7 illustrates the formula for a fully continuous N-year endowment insurance policy value on X at time t. Its prospective formula is expressed as follows. And by factoring out the actuarial present value of the future benefits, the paid-up insurance formula is obtained. This final formula shows the benefit reserve as actuarial present value of a portion that still needs to be collected. For example 8.9, the problem refers to example 8.5, which made use of the premium difference formula, and this involves a fully discrete 30-year term insurance of 100,000 pesos on a person aged 30 and asks for the net reserve at the end of year 10 using the paid-up insurance formula. Now, applying the paid-up insurance formula, we can utilize the values we've obtained from solution 8.5 and plug those values into our solution. Substituting those values, we get a benefit reserve of 0.41. This result confirms that after 10 years, given the paid premiums, the policy accumulates a reserve of 41% of its total coverage value.
Also, we have other special formulas. For fully discrete and fully continuous whole life and endowment insurance, there is a simple relationship between insurance and annuity. As a result, the benefit reserves can be expressed in terms of annuities only or insurances only. In the following, the formulas will be stated for fully discrete endowment insurance. However, they also work for whole life insurances. Just drop the angle m's in all places, whatever m is. Here, for the annuity ratio formula, consider an N-year endowment insurance on age X. Let's start with the prospective formula and then express everything in terms of annuities. For simplicity, assume the face amount is 1. Note that both annuities in the formula terminate at the maturity of the endowment insurance. For whole life, drop angle n minus k and angle n. Hence, we obtain the annuity ratio formula for computing policy values. A of k represents the present value of an annuity at time k. A of 0 represents the present value of an annuity at time 0. This formula is convenient since it involves only two annuities. It is the fastest way to calculate a reserve using a table of annuities and insurances. For example, we need to calculate the policy value at time 23 for a fully discrete whole life insurance of 1,000 issued at age 52, where the mortality follows the illustrative life table with 0.06 interest rate. Applying the annuity ratio formula and substituting the values from ILT, the calculated policy value at time 23 is 0.44. This formula also allows chaining reserves. Since 1 minus V is a ratio of annuities, if we let the right subscript on V indicates the issue age, we have the following. And the same holds. Let's apply this to a problem. Calculate the net premium reserve at time 3 for whole life insurance of 1,000 issued at age 47. We are provided with a table of reserves for a whole life insurance policy issued at age 45. Using the reserve formula given the following, then multiplying by 1,000, we'll get that the net premium reserve at time 3 for age 47 is 45.22.
Now, for insurance ratio formulas, let's start with the annuity ratio formula and then express everything in terms of insurances. Note that both insurances in the formula terminate at the endowment insurance maturity. Hence, we obtain the insurance ratio formula for computing policy values, where 80 is the APV of a unit insurance benefit at time t. Now, let's apply this for an example. In example 8.13, we are tasked to do example 8.11 in the annuity ratio formula using the insurance ratio formula approach. We can see that using the ILT, we can substitute the whole life insurances such that we would get an answer similar to that of what we get in our annuity ratio formula. Now, starting with the premium difference formula for premium ratio formula using A would be equal to 1 over P plus D. But unlike annuity ratio and insurance ratio formulas, you need the interest rate to use this formula. Also, this formula is not particularly convenient to use in conjunction with the ILT as it is the least important of the three special formula. Hence, we obtain the premium ratio formula for computing policy values, where PT is the annual net premium for an insurance sold at duration T, and D is the annual effective rate of discount, replaced by delta for fully continuous policies. Now, to see how this works, we will now proceed to our example 8.15, where we are tasked to find the annual net premium for a whole life insurance of 1,000 on age 47 given certain values on age 45 and 46. To do this, we will first solve for D, or the effective rate of discount, and then use our formula for premium ratio to calculate P47. Hence, we will get an answer of 22.17. Now, the following formulas are for fully discrete insurances of 1 with an A k integer, but can be fully adapted for fully continuous insurance by barring all A and A's, interpreting P's as premium of fully continuous insurances, changing D to delta. And that concludes Lesson 8 on special formulas for reserves and policy values in insurance. This lesson gave us a deeper understanding of how these formulas work and how they are derived from the original equations. These formulas make computations easier, especially for automating calculations when handling data that requires faster processing. I hope you learned something valuable. Thank you.